signals of GPS. In the previous chapter, we discussed about what is GPS, how its function and different components of GPS. In this chapter, we will understand about how the signals of GPS is present, different types of signals, how the measurement can be done to errors that has been caused during the data capture. We will discuss about how GPS can be used in different applications and different navigation systems in the globe. Objectives. The chapter can be divided into signals of GPS, measurement of GPS, application of GPS and various navigation systems in world. GPS system sends their information through microwave signal. The signal system are as pseudo-random code, that is, it is the primary part of GPS. It physically complicated digital number or complicated sequence of on and off pulse. There are two types of PRC signals generally found: Cursor Acquisition Code. This contains L1 signals. It repeats every 1023 bytes and modulates at 1 MHz rate. The CA code is a basis for civilian GPS uses. Precise code. Precise code modulate both L1 and L2, carries at a 10 MHz rate. It is used for military purposes and it is more complicated than the CA code. There are two types of signals, L1 and L2. L1 carries 1575.42 MHz. L1 carries both the status message and the pseudo-random code for timing. L2 carries 1227.60 MHz. L2 is used for the more precise military pseudo-random code. Measurement of errors of GPS. There are a number of sources of error that corrupt these measurements. An examination of these error sources is presented within this section. Satellite clock errors. The satellites contain atomic clock that control all board timing operation, including broadcast signal generation. Although these clocks are highly stable, the clock correction fields in the navigation data message are sized such that the deviation between the SV time and the GPS time may be as large as 1 meter per second. An offset of 1 meter per second translates through a 300 kilometer pseudo range error. Errors were observed to be statistically independent from satellite to satellite with significant correlation over time. Ephemeris error. Estimates of ephemeris for all satellites are computed and uplinked to the satellites with other navigation data message parameters for rebroadcasting to user. As in the case of satellite clock correction, these corrections are generated using a curve fit to the control segments, best prediction of each satellite position at time of upload. The residual satellite position error vector with typical magnitudes in the range of 1 to 6 meters. The effective pseudo and the carrier phase errors due to ephemeris prediction error can be computed by projecting the satellite position error vector into the satellite LOS vector. Relativistic effects. Both Einstein general and special theory for relativity are factors in the pseudo range and carry phase measurement processes. The need for special relativistic correction arises at any time the signal source, in the case GPS satellites, or the signal receiver, that is GPS receiver, is moving with respect to the chosen isotropic light speed frame, which in the GPS system is the ECI frame. Due to rotation of the earth during the time of signal transmission, a relativistic error is introduced known as a Sagnac effect. When computations for the satellite position are made in an ECEF coordinate system, during the propagation time of the SV signal transmission, a clock on the surface of the earth will experience a finite rotation with respect to an ECI coordinate system. Atmospheric effects. The propagation speed of a wave in the medium can be expressed in the terms of the index of refraction for the medium. The index of refraction is defined as the ratio of the wave's propagation speed in the free space to that in the medium by the formula n is equal to c by v, where c is the speed of light and v is the velocity. The medium is dispersive if the propagation speed or equivalently the index of refraction is a function of the wave's frequency. Receiver noise and resolution. The measurement error are also induced by the receiver tracking loops. In the terms of the DLL, dominant sources of pseudo range measurement error excluding multipath are thermal noise, jitter, and the effect of interference. Receiver noise and resolution errors affect carrier phase measurement made by a PLL. Multipath and shadowing effect. One of the most significant error incurred in the receiver measurement process is multipath. Multipath errors vary significantly in magnitude depending on the environment within which the receiver is located, satellite elevation angle, receiver signal processing, antenna gain pattern, and signal characteristics. Hardware bias errors. Hardware bias errors can be differentiated, or there are different types of satellite bias is present. Upon signal transmission, the GPS signals on each carrier frequency and among frequencies are imperfectly synchronized due to the different digital and analog signal paths corresponding to each signal. The timing bias between the L1 and L2 PY code signals is inconsequential for most dual frequency users, since the broadcast clock correction compensate for this bias under the presumption that the user is combining L1 and L2 pseudo range measurements via the ionospheric free pseudo range equation. Other hardware bias is user equipment bias. The user equipment bias errors introduced by the receiver hardware are often ignored because they are relatively small in comparison to other error sources, especially when cancellation is considered. GPS signals are delayed as they travel through the antenna, analog hardware, example RF and IF filters, low noise amplifiers and mixers, and digital processing until the point where pseudo range and carrier phase measurements are physically made within the digital receiver channels. Pseudo range error budgets. Based on the earlier discussion regarding error constituents, we can develop pseudo range error budget to aid our understanding of standalone GPS accuracy. These budgets are intended to serve as guidelines for position error analysis. Position error is a function of both the pseudo range error and the user satellite geometry. Application or uses of GPS. The United States government created the system, maintains it and makes it freely accessible to anyone with a GPS receiver. The Global Positioning System provides critical capabilities to military, civil and commercial users around the world. GPS and satellite image. GPS has been widely used to prepare maps and satellite images, especially topographic surveys and thematic maps. For example, we can have a map that is used by Geographic Survey of India, where the maps are produced for each region, and this map procedure can utilize the GPS system. Road traffic congestion. A navigation device has GPRS receiver for receiving real-time information about or slow average speed on a stretch of motorway, indicating congestion. This device calculates a new itinerary to avoid the congestion based on historically record speeds on secondary roads weighted by the current average speed in the congestion area. For example, we have the Google Maps. Whenever you want to move from one place to other place, it shows different paths and different routes where it will be showing the distance and the time cover, and the conditions are being shown by different colors. For example, we have red color in the navigation where it shows the congestion is to maximum. GPS and defense. Corps uses GPS as a modern defensive purpose like trending and rescued. Accidental purpose. To find and rescue any crash ships and aeroplanes, GPS plays a very important role. For example, we have the Boeing that is being crashed. So, GPS also plays a major role in detecting where the location of a vehicle or where a location of a person is present on the globe. And many of the vehicles in the developed nations have been incorporated with GPS. So, whenever a vehicle is thefted, then with the respective GPS system, we can locate where the vehicle is present. Tectonics. GPS enables direct fault motion measurement of earthquake between earthquake. GPS can be used to measure crustal motion and deformation to estimate seismic strain built up for creating seismic map hazards. GPS and terrorism. GPS is very important to determine the location of terrorist attack. For example, on the surgical strike, Indian intelligence agencies had using the GPS, and Indian Army carried out surgical strike against terror launch pads on and along the line of control on 2016. GPS of mining. The use of RTK GPS has significantly improved several mining operations such as drilling, shoveling, vehicle tracking and surveying. GTK GPS provides centimeter level positioning accuracy. GPS and climatology. GPS plays very important role to prepare weather map and computerized map. For example, GPS allows us to determine what is the weather or that is being present in a particular region, and it also helps to record different velocity of the wind and the direction of the winds that are being going. GPS and tours. Location determines what content to display, for instance, information about an approaching point of interest. For example, we can have, whenever you are using a Google map that's been present, while moving it shows all the indication of the paths that are being present along the way. So, you can have a shop on the right side or a petrol bunk on the left side. So, it shows different amount of characteristics along your path. Navigation. Navigators value digitally precise velocity and orientation measurements. With the help of GPS, roads and paths available, traffic conditions and alternative routes, roads or paths that might be taken to get the destination. If some roads are busy, then the best route to take, banks, hotels, fuel, airports or other places of interest, the shortest route between the two locations, the different options to drive on highway or back roads, etc. are easily getting better result using GPS. Disaster relief. GPS gives us the facility to measure the capabilities of earthquake, flood, wildfires. For example, recently we have the Amazon forest fires. So, GPS or equipped air drone devices will help us to determine what area or what extent the forest fire has been happening and how the velocity of the forest fire has been going on. And GPS also helps us in determining what area or what is the extent of an area a disaster is happening. GPS equi-radios and drop sonders. GPS measure and calculate the atmospheric pressure, wind speed and direction up to 27 kilometers from the Earth's surface. Fleet tracking. The use of GPS technology to identify, locate and maintain contact reports with one or more fleet vehicles in real time. For example, we can have the vehicles that are being located around the globe can be identified with the help of GPS, and the airplanes and or the rockets which are being using, we are embedded them with GPS system so that they are moving in a particular direction. Robotics. Self-navigation autonomous robots using GPS sensors while calculate latitude, longitude, time, speed and heading. Example, the future use of automated cars or the self-driven cars that are being present are majorly depending upon the GPS function, where once the location is been incorporated into the navigation system that's present in the car, then the car automatically takes you from one location to the desired location. Sports. GPS also used in footballs and rugby and different sports for control and analysis of the training load. Surveying. Surveyors use absolute location to make map and determine property boundaries. The surveying and mapping community was one of the first to take advantage of GPS because it dramatically increased the productivity and resulted in more accurate and reliable data. Today, GPS is a vital part of surveying and mapping activities around the world. Distance and height measurement. GPS helps to calculate the distances and heights of different places on the Earth's surface. Automated vehicles. With the help of GPS, location and routes for cars and trucks to function without a human driver. Agriculture. GPS based application in precision farming are being used for farm planning, field mapping, soil sampling, tractor guidance, crop scouting, variable rate application and yield mapping. GPS allows farmers to work during low visibility field conditions such as rain, dust, fog and darkness. Nowadays, the GPS is also incorporated in spreading the fertilizer or chemical pesticides along the field. GPS and fishing. Synoptic maps of the main concentrations of fishermen villages, fishing ports and beach landing points, markets, processing, freezing and transshipment points, coastal landforms can be studied with the help of GPS. GPS and oil leak. GPS tracking technology is helping with the study by examining how currents are influencing by winds and waves and measuring the wind speed to find out how oil would spread from the ocean onto the beach. Many instruments are being used in the study to gather as much data as possible. After data is collected, researchers plan to use 3D pictures of oil transport and hope to come up with more information about oil spills, how to mitigate their damage, and how to protect the environment. Astronomy. Both positional and clock synchronization data is used in astrometry and celestial mechanics calculation. It is also used in amateur astronomy using small telescope to professional observation, for example, which finding extrasolar planets. GPS and forestation. GPS technology makes tree planting more efficient. Deforestation and disappearing wildlife habitat are a big problem in the modern world. Manufacturing industry use state-of-art technology to produce and sell more paper and wood products, but there is a growing concern over the devastation wrought by their methods of obtaining materials. The rate with which large luscious forests are being cut down, the trees are being removed much more quickly than we can hope to replant. As trees take many years to grow to their full potential, one solution, Orientation Man is leading team developing ways to replant forests as quickly and efficiently as possible using GPS technology. Topographic mapping. In the ground control point system, GPS tool used to prepare the topographic mapping of real world. GPS and urban planning. A special GPS technology has been used in urban planning and engineering survey. Cartography. Both civilian and military cartographers use GPS extensively. Global navigation satellite system. Different navigation systems in world. The United States Global Positioning System GPS consists up to 32 median Earth orbit satellites in 6 different orbit planes, with the exact number of satellites varying as older satellites are retired and replaced. Operational since 1978 and globally available since 1994. GPS is world's most utilized satellite navigation system. Apart from GPS, we have different navigational systems that are being developed by different countries. GLONASS. It is being developed by Russia. The formerly Soviet and now Russian Global Navigation Satellite System, or GLONASS, is a space-based satellite navigation system that provides a civilian radio navigation satellite service and is also used by Russian Aerospace Defense Forces and is the second alternative navigation system in operation. GLONASS became operational in the year 1993 with 12 satellites in 2 orbits at the height of 19,130 kilometers. At present, there are a total of 27 satellites in orbit and all are operational. Galileo. The European Union and European Space Agencies agreed in March 2002 to introduce their own alternative to GPS called Galileo Positioning System. The Galileo became operational on 15th December 2016, Global Entry Operational Capability, at an estimated cost of 10 billion euros. The system of 30 MEO satellites was originally scheduled to be operational in 2010. The original year to become operational was 2014. The first experimental satellite was launched on 28 December 2005. Galileo is expected to become compatible with the modernized GPS system. The receivers will be able to combine the signals from both Galileo and GPS satellite to greatly increase the accuracy. Galileo is a global navigation system available for civilian and commercial use. The fully deployed Galileo system will consist of 30 operational satellites and 6 in orbit pairs. As of now, 22 out of 30 satellites are in orbit. Galileo started offering early operational capability from 2016 and is expected to reach full operational capability by 2020. Beidou. Beidou is a satellite navigation system of China. It has total 22 operational satellites in orbit and a full constellation is scheduled to comprise 35 satellites. Beidou has two separate constellations, Beidou 1 and Beidou 2. Beidou 1, also known as first generation, was a constellation of 3 satellites. Beidou 2, also known as Compass, is the second generation of the system. Beidou started as now decommissioned Beidou 1, an Asia-Pacific local network on the geostationary orbits. China has indicated their plan to complete the entire second generation Beidou navigation satellite system, formerly known as Compass, by expanding current regional Asia-Pacific service into global coverage by 2020. This Beidou 3 system is proposed to consist of 30 MEO satellites and 5 geostationary satellites. A 16 satellite regional version covering Asia Pacific areas was completed by December 2012. Global service was completed by December 2018. It became operational in the year 2000 and offered limited coverages and navigation services, mainly for users in China and neighboring regions. Beidou 1 was decommissioned at the end of 2012. It became operational in the year 2011 with a partial constellation of 10 satellites in the orbit. Next generation of it is Beidou 3. The first BDS 3 satellite was launched on March 2015. As of January 2018, 9 BDS 3 satellites have been launched. Beidou 3 is expected to be fully functional by the end of 2020. Regional Navigation Satellite System, NAVIC, India. The Indian Regional Navigation Satellite System, IRNSS, which was later given the operational name of NAVIC or Navigation with Indian Constellation, is the regional satellite navigation system of India, launched and operated by the Indian Space Research Organisation, ISRO. IRNSS covers India and nearby regions extending up to 1500 km. The NAVIC or Navigation with Indian Constellation is an autonomous regional satellite navigation system developed by Indian Space Research Organisation ISRO, which would be under the total control of Indian government. The government approved the project in May 2006 with the intention of the system completed and implemented on 28 April 2016. It consists of a constellation of 7 navigational satellites. 3 of the satellites are placed in the geostationary orbit and the remaining 4 in the geosynchronous orbit to have a larger signal footprint and lower number of satellites to map the region. It is intended to provide an all-weather absolute position accuracy of better than 7.6 meters throughout India and within a region extending approximately 1500 kilometers around it. A goal of complete Indian control has been stated, with the space segment, ground segment and user receivers all being built in India. All 7 satellites IRNSS 1A launched in 1st July 2013, IRNSS 1B launched in 4th April 2014, IRNS 1C on 16th October 2014, IRNS 1D on 28th March 2015, IRNSS 1E on January 2016, IRNSS 1F on 10th March 2016 and IRNS 1G on 28 April 2016. Of the proposed constellation were precisely launched from Satish Dhawan Space Centre. It covers India and a region extending 1500 km around it, with plans for further extension. An extended service area lies between the primary service area and a rectangle area enclosed by 30th parallel south and 50th parallel north and the 30th median east to 130 median east, 1500 to 6000 kilometers beyond borders. The system at present consists of a constellation of 7 satellites with 2 additional satellites on ground as standby. The constellation was in the orbit as of 2018 and the system was operational from early 2018 after a system check. NAVIC provides 2 levels of service, the standard positioning service which will be open for civilian use and the restrictive service, an encrypted one for authorized use including military. There are plans to expand NAVIC system by increasing constellation size from 7 to 11. QZSS. The quasi-zenith satellite system is a regional satellite navigation system from Japan which is still under construction by the Satellite Positioning Research and Application Center, Japan. As per plans, the QZSS constellation will have 7 satellites, out of which 4 are already in orbit. The quasi-zenith satellite system is a 4 satellite regional time transfer system and enhancement for GPS covering Japan and Asia-Oceania region. The QZSS service were available on the trial basis as of January 12, 2018 and were launched in November 2018. The first satellite was launched in September 2010 and independent satellite navigation system from GPS with 7 satellites is planned for 2023. Augmentation. GNSS augmentation is a method of improving a navigation system's attribute such as accuracy, reliability and availability through the integration of external information into calculation process. For example, the Wide Area Augmentation System, the European Geostationary Navigation Overlay Service, the Multifunctional Satellite Augmentation System, the Differential GPS, the GPS Aided Geo Augmentation Navigation (GAGAN) and Inertial Navigation System. DORIS. Doppler orbitography and radio positioning integrated by satellite. DORIS is a French precision navigation system. Unlike other GNSS system, it is based on static emitting station around the world. The receiver being on the satellite in order to precisely determine their orbital position. The system may be used also for mobile receiver on land with more limited usage and coverage. Used with traditional GNSS system, it pushes the accuracy of position to centimetric precision and to millimetric precision for altimetric application and also allows monitoring very tiny seasonal changes of earth rotation and deformation. In order to build a much more precise geodesic reference system, Global Positioning System, United States. Summary. GPS is the main navigation system used by common civilian and military organization. Apart from GPS, various countries have developed different navigation system. Navigation system has been developed in a way that every electronic device can have a receiver and a navigation application can be used on a click. GPS has a big role in disaster management and risk assessment.